Hello, Algebra 1 honors. This is our last section in Chapter 8 where we're dealing with quadratics and exploring how to graph them. Our last section here is what we're going to do is we're going to compare linear models, exponential models, and quadratic models. Sorry, something's on my phone here. There we go. Just to kind of review a linear model, the format or kind of the formula for linear models was y equals mx plus b. And of course, when you graph a line, you get a line, right? Well, exponential models people have a hard time, excuse me, sometimes remembering what these models look like, and the setup form. The setup is y equals a b to the x power. So your variable there is the exponent. And when you graph these exponential functions, if it's a growth one, it tends to be small, small. And then when it starts growing, oh my goodness, it really grows. And then the quadratic models, which are the ones we've been dealing with in this chapter. Quadratic model, it has this format right here, y equals ax squared plus bx plus c. Now that covers kind of all the possibilities there. That's the standard form. So I shouldn't say it covers all the possibilities, but that's the standard form. But I want you to recall that, when we first started graphing quadratics, some of the most basic ones didn't have an x value, an x term. They didn't have a constant term. So, sometimes you just have x squared and maybe a number in front of it. But anyway, regardless, the graphs for these are parabola shaped. So what we're going to spend the rest of this lesson doing is comparing different facets of these three different models. And also, we're going to write equations for them, which is going to be kind of cool. Let's start out. We're going to use a graph to identify as linear, exponential, or quadratic function. And this is pretty much a piece of cake. Plot the points, see what shape you got. Now this one, initially you might think, oh, maybe it's linear, but you can see there's a bit of curve to it. Now, based off of this data, it can be a little bit tricky determining if it's the difference between an exponential and a quadratic. But you got my assurance that we'll give you enough information with the points that if it's a quadratic, you'll be able to tell because you'll have the change in direction. So it turns out this graph would actually follow that sort of path like so. And you've got the asymptote there that it doesn't cross. And it's exponential. And also, one way to verify that it's exponential and not just trust that it is to look at your y values. And there's going to be a pattern there. What's the pattern? If you go to 1/4, then 1/2, and 1 and 2, well, pattern is that they're multiplying at each stage, in this case by 2. I don't know if you remember, but when we were dealing with exponential functions, that amount that they multiply by each time is actually the base of your exponential function. So this would be probably y equals 2 to the x power. And yeah, actually that would be it, because anyway, I can tell by the y-intercept. All right, next up, plot these points. Well, that looks like a line to me. And you really don't need to verify it, but with linear equations, you're going to see a pattern as well. And the pattern, I'm looking at the y values. Yeah, you're adding 1 each time. Or you could be, adding some other value, but in this case, adding 1 each time. That turns out to be your slope as well. So anyway, I believe the equation for this would be y equals 1x, or x plus 1, because my y-intercept's 1. But anyway, and then on the next one, let's plot it out. And that's pretty clearly a parabola. And a pattern that you can notice from the data is that the y values are going down, and then they start creeping back up. So none of the other graphs do that. They follow constantly getting bigger, constantly getting smaller, but this one kind of changes directions. All right, so some other things we can do. It says explore the following equations and corresponding table of values. And I've talked about that a little bit here, but let's talk about it some more. Y equals 3x plus 5. Across for the x's, you're going up by 1 each time, adding 1. And that's pretty common, But for the y values, what's the pattern? The pattern is they're adding 3 each time. Okay, so what you can do, what I can assure you of, is that if you're adding the same amount, each time, you're looking at a linear model. Take a look at 1/2 times 2 to the x power. That's an exponential. And notice the pattern. You're still going by 1 across the top here in this example. It is important to notice that. And what's the pattern going across? Each time it's repeated what? It's repeated multiplication, and in this case by 2. So to determine if it's an exponential function or not, you're going to look for repeated multiplication, or the fact that they multiply the same amount each time. And that's going to be exponential. Whoops, sorry. Exponential. And then this next one, the quadratics, I already kind of talked about how, well, first let's verify adding 1 each time. Okay, so adding 1 each time. But I already talked about how it'll change direction, going down, then back up. That's a good indicator that it's a quadratic. But there's something interesting about it. It turns out, well, they call this 3 over here, it's called the common difference on the linear model. Common difference, the difference between the newest and the previous is 3. Well, it turns out that quadratic functions, if you look at their first pattern as far as their differences, or what they're adding each time or subtracting, it goes, let's see, -3, -1, 1, and then +3. And what's fascinating about quadratics is, there's no real pattern here when you look at an addition or subtraction pattern. But if you take the second difference, there will be a pattern. And what are they doing? They're adding 2 each time. Isn't that cool? So every quadratic, the second difference, if you find it, calculate it, it's going to be consistent. So quadratic. And yeah, the second difference will always be consistent. Okay. But I typically, for the most part, can just, you can be pretty sure about it by seeing that the data goes, down then up or up then down. Okay, well, let's flip it over, see what else we got. Oh, hold on just a second. Don't worry, I've got the back page here. You were worried, weren't you? All right. So, next up, we are tasked with writing an equation for the function, okay? Now, to do this, we're first going to have to determine which of the 3 models it is. Is it linear, exponential, quadratic? But then from there, we're going to have to use the equations for them to write the equation, use the models for them to write the equation. So just a reminder, linear will be y equals mx plus b. We'll use that to help us write our equation. Exponential, we'll use y equals a times b to the x for writing those equations. And then for our quadratic functions, we're just going to stick with the basic ones. And we're just going to use y equals ax squared. Stick with the most basic types. All right, so for our first example, let's see. So they're going by 1 across the top, 1 across the top, 1 across the top. Okay, so we're good in that respect, 1 across the top. And then we look at the y values, and what is the pattern going across here? Could be they're subtracting 2 each time, but that quickly fails. So another way to go from 4 to 2 would be to divide by 2 or multiply by a half. So 4 times a half is 2, times a half is 1. All right, we found it. So it turns out this pattern here is multiplying by a half. And when you have repeated multiplication, what type of function is it? Well, it's exponential. And then from there, what you can do is, well, there's actually a couple ways you can do it, but probably the easiest way to do it is to, what you're repeatedly multiplying is your base, but then what's tricky is, so you have y equals a 1/2 to the x, okay, that's the setup. But we need to find out what a is. And if you remember from the alien example that we did when we first worked with these, the alien, well, how many aliens landed? There was 1. And so in that model that we did with the alien, you would have 1 alien, but then it doubled every hour, I think we did. So we put a 1 there, a 2 there. Well, the a is the initial amount. It's the starting amount. But it's also your y-intercept. So you can look at 0, 1 there, and that's a shortcut for getting to A, is to look for the y-intercept there. So it turns out our final answer is just going to be 1/2 to the x, or just 1/2 to the x power. Now another way you could do this is you could take one of the other coordinates, one of the coordinates, doesn't matter which one, but you can plug in for x and y, and then you can solve for A, which is not a bad way of doing it. You've got your nice calculators now, so you could put in, you could put in 0, 1, 0 for x, 1/2 to the 0 power is 1, and then 1 in for y. You quickly find that A is equal to 1. So that's another way to do it. If for some reason you're not given the y-intercept, you could just insert an extra coordinate and help you solve for what you're missing. All right, let's look at our next relationship here. Okay. Oh, I already know what it is. It's going down, then up, okay? And you can double verify that by getting the second difference to show you that it is in fact a quadratic. So we got -6, -2, 2, 4, and then do it again, and the pattern is adding 4 each time. Now quadratics are kind of odd because you might think that 4 is part of your equation, but that's not the case. We're going to be focusing on the most basic types of quadratics, and here's how you're going to do it. So, let me write that down first. So we know it's a quadratic, but because we're just going to focus on the simplest types, quadratics always have the x squared, but we need to determine what A is, what A's value is. So to do that, we'll just, so we need, let me do a little explaining here. We need to find A, and A is not going to be the y-intercept. Our y-intercept is 0, and that's not what that's going to be, because it would wipe everything out. But to find A, we're going to substitute an easy x and y. And we are totally going to avoid that 0, 0, because that's going to wipe everything out and not be helpful whatsoever. So, need to find A. Let's substitute an easy x and y. So I think 1 and 2 is pretty easy. So we'll go 2 for y, 1 for x. Simplify that down, we'll get 2 is equal to A. So the equation for this quadratic is y equals 2x squared. Just like so. Let's look at the next example. Let's see, the pattern, if it's a multiplication pattern, it's going to be a messy one. What you can do is do new over old to find out, what the multiplication pattern is. It'd be multiplying by 5/7, but that will not get you the next term. So maybe this is an addition pattern, so adding 2. There we go, sure enough. Adding 2 is the pattern, and addition makes it, an addition pattern makes it linear. And we've got y equals mx plus b. Well, the repeated addition is your slope, as long as you're going by 1. If you happen to be going by 3's up there, your slope would be 2, and then you divide by 3, which is kind of cool. But no, this is going by 1 across the top, so our slope is going to be 2. So we'll have y equals 2x plus b. Now, if you're lucky, you'll remember that your b is your y-intercept, so you can get a -1 there. But maybe I should go ahead and work it out, because you won't necessarily always have the y-intercept. Kind of explain that up here on that one, but let's go ahead and work it out here. If you don't have the y-intercept, you're going to need to solve for it. And what you can do is just take any coordinate, temporarily substitute it in for x and y. Solve for b. Whoops, sorry, I'm a little sleepy. Get b is equal to -1. And then we can write out our equation, y equals 2x minus 1. Just like that. And finally, there are all sorts of real-life models that are represented by linear, exponential, and quadratics. And here's one example. The data we have here is speed and breath rate. And I can't remember where this came from. It seems like it was a cycling example, like the speed that they were bicycling and then their breath rate. Anyway, let's look and see if we can find a pattern here. We're going by 1 across the top. That's good. And then our y value here, what are they doing? Okay, it's going up pretty consistently. So let me find the difference there. And the difference would be, what would it be? Let me grab my calculator real quick. Hold on just a second. All right, so I got my calculator. 57.1 minus 51.4 and I get 5.7. Let's see if that works to get the rest of the values. So 57.1 plus 5.7. Does that get me 63.3? No, it does not. I'm not sure if you can see that very well. 62.8. So it does not match. So this is not an addition pattern, which I kind of thought it was. You know, I had to get my calculator to double check. But it is not an addition pattern. So what it might be is, I'm not thinking that it's a quadratic because it's not going up then down. It's not changing direction. So I'm thinking this is probably an exponential function. But it's not an easy one to determine just by looking at it casually. And when that happens, when it's not easy to find out what they're multiplying by each time, just do new over old. Take the new value, divide it by the previous value. So new over old. So I'll do 57.1. Divided by 51.4. And I get a rather lengthy decimal there. Okay. Well, let's see if we can either see if we can multiply by 1.11 approximately. Well, actually, I'll leave that in my calculator. And I'll times it by 57.1 and see if I get 63.3, if that makes sense. Okay. And I get 63.43, which is, you know, pretty close. It isn't exact, but it is close. Let's try 70.3 and multiply by 1.11089494.2, and I get 78.0959. So that's pretty close to 78.0, but it's not quite working out exactly. I think there's just a bit of a rounding error that we're coming across here. Let me try one more thing. So we did new over old. Let's do new over old in a different spot. So 78 divided by 70.3. 1.11. Yeah, I'm gonna if you come across a problem like this where it's close but it's not exact, you know, ask me about it. But I'm gonna say, because what I got earlier was about 1.11. It was a little bit above. This is a little bit below. I'm going to generalize and say that the pattern here is approximately multiplying by 1.11. Now there's some rounding issues here, and it could be when I wrote the problem, but it appears that multiplication pattern most closely represents the pattern. And because of that, we're going to think of it as exponential. So for an exponential, we'll go y equals, and then we go a 1.11 approximately. That's our base. What we're multiplying by is our base. And now a is our initial amount. So we look for our y-intercept. Oh, shucks, we don't have it. So what we're going to have to do is take an easier one, substitute in for y and for x, and then you're going to solve this. Now, I got to warn you, I'm not going to put that in my calculator and then round it and write that down and then divide that rounded amount. I'm going to divide the whole thing. And I'm going to use my fancy calculator to divide that whole thing. Oftentimes, if you round in the middle of a problem, it compounds, it exaggerates you know, the slight error that you're introducing by rounding, and then it gets you a more significant error. So I'm going to put that all in my calculator there. 51.4 divided by, and then I'm going to do 1.11 to the 20th. Do parentheses 1.11. And I get, if I round, 6.38. 6.38 is my A value. And now that I've found my A value, I can write out my equation. Y equals 6.38, 1.11 x. So when the numbers aren't the nicest in the world, it can be a little bit tricky. All right, so class, there's your practice there, page 465, 1 through 25. Thanks for watching.